All right. Hi, everyone. Welcome to the soft talk section. So we are going to have like 10 interesting talks from the speakers from academia and as well as industry. Let's begin with the first talk. The title is Showtime CPU Timing Attacks with the Human Eye. And the speaker will be Antun Promo from the QUVAT.
Thank you, Mr. Chairman. Yeah, so this talk is Showtime, and what I'm promising you is a show. So that's one thing. And it will also be centered around the human. Because something I've noticed over the past few months is that humans are getting displaced by machines. So machines are getting good at tasks we humans used to be good at. So I want, with this short talk, give power back to the human and do things that previously only machines could do. And that's looking at things happening at the nanosecond scale. And for that, I'm going to need you. So the topic is computation. And when we compute, we see that the business proposition in, for instance, cloud computing is to put as many tenants as possible, so as many security domains as possible on the same physical machine. You also see that on a smartphone. You also see that in a web browser, for instance. So if you run, if you visit a website, that's code running on your machine, and then you can have co-tenancy issues. Now, the nice part is, for defenders, that side channel attacks exploit these minuscule timing differences. So these are timing differences in the order of tens of nanoseconds, maybe hundreds of nanoseconds. So these timing differences are very, very small. And so what you could conceive as a countermeasure to block all of these attacks is to just disable access to these high-resolution timers, because you need high-resolution timers to measure high-resolution things. And this is something that's been proposed in academia and is actually deployed in browsers. So there are no high-resolution timers in browsers anymore, and people are looking at implementing similar things on regular CPUs. And the question that we asked is, well, can't we just amplify these timing differences? And for that, I told you that I was going to put the human in the loop, and the human, that's you, the audience. And what we basically did is we found a way to amplify these timing differences from tens of nanoseconds to timing differences that a human can distinguish. And we're going to put that to the test with the following demo, which I hope will work. All right, so we're going to calibrate now. So what I'm going to show you is a cache hit. Okay, so you see show time, you see show and time appearing at the same time. This is a hit, okay? We're going to look at another hit. And a final one where show time, they appear at the same time. This is what a hit looks like. Okay, you're human, you can learn this. So now let's look at what a miss looks like. All right, let's do that again. And one more time. All right, let's look at another hit then. And now another miss. And now it's up to you. Let's go. Three, two, one. Nice. Correct. Let's go for one more. 3, 2, 1. Nice. Good humans. One more then. 3, 2, 1. All right. Three, two, one. This was a hit. One more. 3, 2, 1. This was a hit. So some of you did a very nice performance, others could use some work on the reflexes, but when we did this in a controlled study with actual 15 humans that we exposed to a lot of these, We saw accuracies 98%, 99%, and some people I'm even doubting whether they're human at all because they had an accuracy of 100%. And with that, I want to thank you for your participation and hand over to the next speaker. Thanks.
Hey, let's thank the speaker. So we come to the next talk, Change for Perspective, Data-centric, Identity First, and Threat Informed by Claudine Mandy from Asymmetric Systems.
Good evening, everyone. I'm Claude Mandy from Asymmetric Systems. We are a data security startup that came out of UT Austin. I'm here to talk about changing your perspective and kind of looking at things a little bit differently. And hopefully that some of you leave the room and kind of change some of your research focuses as well. Now, it's interesting for an academic kind of startup to present a chart without a y-axis. But the thing that we're kind of looking at is this is your organization. No matter what the company is, what the y-axis is, we see the same trends, the same universal problems. Organizations are collecting more data than ever before. They have more human and non-human identities than ever before. They want to do more with it. ChatGPT is kind of wanting to connect to every data set. And more people want access. So we have more identities, more data, more permissions, more operations on data. In 5 minutes, I would have had to present 15 slides. All this data and collection is important because at the end of the day, data is important. It's about people. It's about money in a digital economy. It's about the intellectual property that makes companies successful. And it's heavily regulated with fines and penalties that we've seen today for not protecting it. You know, Meta's in the news for the biggest fine in history. And that data is a target. It can be monetized if it gets in the wrong hands. So the result of all of this is, you know, more identities, more permission, more data, a bigger boom, a bigger event that happens. So the importance of all this data is obvious, right? We need to be better at protecting the things that we care about the most. And if you look at the background, that's actually a simulation from one of our products that shows you the extent of data that we're tracking within a single customer. So that successful attack, that blast radius, all those blue dots are actual data stores that a single company is trying to protect. But the challenge is we still play by the attacker's rules, right? We're forced to react to their every move, and then they change the rules. You know, we kind of do all the stuff to patch vulnerabilities, they find a new way, and then there's always a way to do that, or they just have a simple fish to get access to it, a compromised identity. You just need to look at the latest Verizon data breach investigation report. You know, credential phishing compromise is still the single most effective way to get access to your data. And the solution isn't this. It's quite confronting to look at it from a vendor, but there are thousands and thousands of more security vendors that come onto this. We're just one of those. So we really need to start thinking about a different way of approaching this problem. And adding more tools and more complexity when we forget about the basics isn't helping anyone, especially when we layer those defenses in from the outside in. We look at the vulnerabilities, we try to patch those, we kind of go to the next layer, look at the applications, the vulnerabilities, and try to patch that. The kind of challenge that we want to leave you with, it's time to change that perspective and kind of invest in security from the data, focus on what we're protecting, and secure our organizations from the data out. And that starts with, firstly, identifying what data we have, protecting it with the access controls, the biggest things that we have to protect that data, and being threat-informed to detect and respond to activity at that data layer. What modern security looks like for us is kind of taking this approach of visualizing your data, centralizing or being data-centric, identifying what it is, what it looks like, and finding better ways of protecting that through your access controls, and then layering on the threat detection and the threat inform from that data layer out. So kind of key takeaways that I want to leave you with is we need better tools in this space that are able to identify and classify your data, are able to assess who has access to your data and who is using it. These are hard problems in the cloud, in the environments that we have. And thirdly, we need to reduce the risk of unused data and permissions and being able to find better ways to monitor and alert on the anomalous behavior of the data. Thank you for joining my short talk. If there are any questions after this, come find me. I'll hand over to the next presenter.
Thanks to the speaker. So the next talk will be, Is Everyone Equally Trustworthy in Practice by Andreas from TU Darmstadt.
Hey, hello. I'd like to share with you today some of the insights I and my colleagues Thomas Ajit and Tosin at Technical University of Darmstadt had when discussing the question if it's really such a good idea to consider that everybody is of equal trust in settings of multi-party computation. So, jumping into a classical example here, let's take credit scoring. On the one side, we have some customer, and this customer wants a credit card issued at their bank. Now, the bank doesn't just hand this out, but actually wants to know if they should give this credit and go to some credit scoring company. This maybe also append some data they additionally collected about this customer, and now they get a credit score back, and finally may, in the worst case, say the customer that they actually don't give the credit. But what we actually would like to have is some kind of private credit scoring, where we still have the system where all parties give their inputs, get their outputs, but at the same time the customer is worried about their sensitive data. The bank must also somehow protect the customer's privacy, and the owner of the machine learning model wants to protect this model as its intellectual property. And one possible solution here is to employ multi-party computation, where those three parties conduct a secure protocol which doesn't leak anything but the actual outputs. So in multi-party computation, we have to select some setting where we want to be secure in. Most famously, the semi-honest setting or the malicious setting. In the semi-honest setting, all the parties follow the computation honestly, but try to find out as much as possible. In the malicious setting, each party is essentially free to do whatever they want. So the semi-honest setting, trivially, is a much weaker security setting, but at the same time, it's much cheaper than the malicious setting, where we often have a larger overhead. So we asked ourselves if these are really the appropriate models in our or even many other practical applications which are asymmetric. Because on the one side, the customer, it's hard to believe that the customer always acts in a semi-honest manner. At the same time, larger institutions like the bank could have some higher degree of trust where people trust them to be semi-honest at least. So what we are actually doing is that we try to leverage asymmetric trust, where we consider some fixed subset of the parties as the ones which may behave malicious, while others are assumed to be semi-honest. And what we hope to achieve here is get higher security guarantees than in the plain semi-honest model, while at the same time being more efficient than in the malicious setting. And I have to mention that this already has been done, for example, in the two-party setting by the work of Muse and subsequent works on an application point of view. But what we want to do here is to consider the three-party setting, which usually has higher performance. So we consider three non-colluding parties, where one fixed is malicious. We also want to consider some pre-processing phase, so that then, once the inputs are given, we have a much faster online phase to really push the practical applicability of our protocols. And we want to consider the case which has been done in some of the state-of-the-art works, where one party acts as a helper, which is offline for most of the online phase, which pushes the practical efficiency of the actual protocol. So if we look at such a setting, the state-of-the-art protocols for the semi-honest case and the malicious case are, for example, Astra and Swift. And what we found out is that in our setting, now it depends on if the helper is a malicious party or one of the other parties, an evaluator is a malicious party. And we see that we are really able to achieve some nice trade-off in between. So we see that if the helper turns malicious, after amortization, we get basically no overhead over the fully semi-honest protocol Astra, but at the same time, even if one of the evaluators gets malicious, where much more could actually go wrong, we still get a nice 33% efficiency improvement in the setup phase compared to the fully malicious protocol of Swift. So if you're interested in this kind of research direction or have any questions, please come forward and ask me after this session, or also via my email, Hoover app, or any other possibilities there are digitally. Thank you.
Thanks to the speaker. So the next talk will be a TikTok deep dive, The Numbers Speaks for Themselves, by PJ from the COCA.
All right. Well, good afternoon, everybody. Vijay Pawar. I had a product at Quokka. It's a very interesting name. You should look it out, check it out, quokka.io. Quokka is actually a marsupial, cuddly little furry animal out of Australia, but nothing to do with this talk. It's just that we have an offering that is on the consumer side, which actually goes into, which is very pertinent to this talk, which is about mobile application security testing. Okay. Company has deep roots in academia. Papers have been written. You can check it out on our website as needed, because this is a 5-minute talk, where we are presented at Black Hat and other such conferences. What I'm going to talk about is what's happening nowadays, right? What's top of mind is what's happening with apps like TikTok, right? If you have kids, I know my kids, everybody has that. I don't have it, but there are tons of people, right? 1 billion downloads. And very soon here, 1 billion people actually using an app like TikTok, right? So let's get inside, some of the deep analysis that we did. So by the way, when we look at applications, be it on the Play Store or the App Store from iOS, we actually run it through our analysis engines. Okay, so a lot of things going on under the covers. There's forced path execution. We take it through different mechanisms to throw random variables at it, fixed variables at it, and try and understand what's going on with this particular application. So, as you can see out there, okay, TikTok from a permissions point of view, really high in terms of the permissions that it's asking for. But what's really important, as you can see here, is ByteDance. ByteDance is the parent company, okay, of TikTok. What people don't see or not going after is the 3% of apps that actually use the ByteDance SDK, okay? And as you can see out here, they're very close in the permissions that are asked by TikTok, okay? So we took our analysis through, our big database of Android apps and noticed that 3% of those apps were using the ByteDance SDKs. 77% of the apps in the game category were actually using the ByteDance SDK. Okay, so permissions, right? Everybody knows about the regular permissions, contacts and access, and there are deeper ones when it comes to access to, let's say, your text messages. But we talk about TikTok, but there are, and again, just for reasons of not publicizing these applications which are out there, there are a couple others which are way more invasive, okay? And these are, you can imagine, which are the top 2 social apps out there, and they're pretty invasive out there. And not just TikTok, after that, a slew of the top apps that are out there, in the app stores. If you look at the security risks, TikTok is lower than some of these other ByteDance apps. I'll give you one, CapCut. If you go today and you look at the editors that are out there, okay, where you can generate all these fantastic TikTok videos, CapCut is one of them. That is from ByteDance, okay? Again, from privacy to security, okay? These can actually get to your storage, okay, especially on Android. They can actually look at your network traffic, okay? So they go to different destinations, okay? So it's very important to understand that it's just not one. There are many other social apps out there. We also found that there were 5 other apps, okay, which are more insecure than TikTok, okay? So if you look at all the downloads that are happening, like I said, a huge number of downloads for TikTok, 1 billion, right? But if you stop them, is that going to stop all this data exfiltration, okay, invading on our privacy? Well, not really, because if you look at that, 100 million were actually 38% of these ByteDance built SDKs. All right, and I'll close it out. So this is minus games. Gaming is actually where a lot of this goes on. And as you can imagine, right, people love to download these new games, especially the kids, and there you go. There goes the data and your privacy and their privacy. So in closing, TikTok asks for twice more data than the average social app. Apps made by ByteDance, okay, consistently ask you for more information. It is the number 3 invasive app. But again, at the same time, you got to understand the implications, not just of one top app out there, but what's happening in the ecosystem. And it is our job here, at least at Quokka, what we are looking at is making people aware. We're getting back into the OS vendors, the firmware vendors, to see how we can block it deep down under at the root. So thank you. If you want to check us out at quokka.io. Thanks.
All right, thank you, speaker. So next talk will be private mail, privacy-preserving framework for secure emails by Renit from TU Darmstadt.
Thank you very much. Good early evening, everybody. I would like to share our idea of privacy-preserving framework for secure emails. And let me start with the general mail processing model. So we have a sender on the left side who wants to send an email to the receiver on the right side. So the sender has a Gmail account here, and the receiver has Outlook. And so the process basically goes that the email goes from the sender to the outgoing email server of Gmail, and then to the incoming email server of Outlook, and finally the receiver can fetch the email using the IMAP protocol. And in this process, normally the copy of the email is stored on both of the servers. And I want to point out here that nowadays it's very normal that each channel has some kind of encryption between each of the hubs, but the privacy issue lies in the fact that each of the server has the copy of the email. And so any malicious behavior on the server or the data breach could compromise the email security. And we have some solutions to this. So we have a PGP or SMIME, which are based on end-to-end encryption. But I would like to list some of the drawbacks that come with these solutions. So first is the obvious that there is no way to do processing on the server side without actually leaking the decryption key to the servers. And then these solutions require some sort of certificates and key management, which basically lead to usability issues, which have been studied quite broadly already. And then finally, these systems are just not widely adopted. And then we also have some practical problems that come from the drawbacks. So since there are no server-side processing, keyword search is impossible on the server side, which you need if you use a mobile phone, for instance. And then also spam detection is not possible anymore on the server side. Also, companies are not able to detect data exfiltration as they usually could. And finally, on top of the key management, we also have the issue that we need to somehow share and distribute our public key to our colleagues or other possible people who want to send us email using these systems. So let me move to our idea, which is based on a technique called secret sharing. So now the sender secret shares the email into 2 random-looking strings, such that if they are both combined together with a simple XOR operation, we can actually derive the original email. And now let's say that the sender also has an email account at Yahoo, and also the receiver on top of the Gmail and Outlook. And now the both shares go through each of these different paths to the receiver. And here, each server now has a copy of the secret share, which as itself doesn't leak any information about the email itself. So now we have solved the problem. And only assumption we need to point out that, of course, the Yahoo can now or is not allowed to collude with the Gmail or Outlook servers. With this simple idea, we can now actually accomplish the features we were missing earlier. So with this technique called secure multi-party computation, also known as MPC, we can, for example, perform the keyword search using methods. And by definition, the MPC is going to protect the input values and only going to output what we want to know if the keyword was found in these emails. And I also listed some of the use cases here on this slide, which basically follows from the earlier slide. And finally, I would like to show our implementation of a Thunderbird plugin, which demonstrates how usable our system is. So by simply clicking one button and defining a couple email addresses, we can send the email using PrivMail. And then on the receiver side, we just implement a simple view box which shows the original email after the shares are combined together. So with this, I would like to finish my short talk. Thank you very much for your attention, and I'm looking forward to the future discussions with you.
Thank you. So the next talk will be how to avoid unfair exchange, adapter signature security revisited by Paul from FAU.
Hi, welcome to my talk, how avoid unfair exchange, adapter security revisited. This is a joint work together with Dominik, Pratik, and Aravind. Okay, what are adapter signatures? Adapter signatures or scriptless scripts can be seen as some kind of verifiable witness encryption of a signature scheme, and they were actually designed for the payment channel setup, where we can see, okay, we have two users, A and B. User A wants to learn a witness, user B wants to learn a signature, and now we make some kind of fair exchange between these both. This is a three-step protocol where B sends a statement to A, then A can create a pre-signature on the statement. This pre-signature can be seen as a witness encryption, and it sends back the pre-signature to B, where B can decrypt the pre-signature using an adapt algorithm if he knows a witness small y. Then, because we are in a blockchain setup, B will publish the signature to a blockchain to get a payment. But now A can learn the signature, and he has an additional algorithm that is extract. And then with extract, together with a pre-signature and a full signature, you can learn the witness that was used to decrypt. Now, people are using these adapter signatures in blockchain setups where the blockchain has no scripting ability. But the problem is the current definitions are tailored to payment channels, but people were using them aside from payment channels. I will now propose three protocols that each use adapter signatures that have concrete, secure instantiation if they are instantiated using Schnorr signatures. But if you use a general adapter signature, security won't hold. My first example is a paper, Foundations of Coin Mixing Services. It was published to CCS 2022. And in a coin mixing service, you have users A and B that are interacting with a hub to promise to a puzzle and to solve a puzzle, where we can see a puzzle promise as a pre-signature and a puzzle solve as a full signature. And they have a security guarantee, namely unforgeability, that says, okay, when I have one puzzle promise, I can get at most one puzzle solve. We found a counterexample of an adapter signature scheme that I posted here. It's quite simple. So instead of pre-signing once, you're pre-signing twice on the same message. As the pre-signatures are randomized algorithms, these sigma P1 and P2 are different. And whenever we adapt, we ignore the second component and adapt only the first one. Okay, what could an adversary do? An adversary learns one pre-signature, sigma P1 and P2. He flips it to be sigma P2, P1. Then he runs adapt on each of them, and running adapt on each of them, he learns sigma 1 and sigma 2, and they are not equal. Therefore, if this protocol is instantiated with our adapter signature scheme, it's clearly insecure. Our next example is work cryptographic Oracle-based conditional payments. In this work, the authors tried to create a verifiable witness encryption based on adapter signatures. The problem here is that different to payment channel setups, the encrypting party A samples a statement and creates a pre-signature. Therefore, this party does not have any incentive to sample the statement in an honest way, and therefore, it's not clear that user B can adapt the pre-signature. We found out that this is actually, that's basically our attack. And we found out that we can construct an adapter signature that has this leakage, but is still secure in the current settings. Our third counterexample are generalized channels. They were proposed at AsiaCrypt 2021. A generalized channel between user A and B can be seen as a sequence of committing transactions. And each of these committing transactions, the output can be spent either by A and B after some time, or in a punishment setup by a user, let's say A, if he knows a witness of B, or B if he knows a witness of A. Now we have a problem with the security definitions of adapter signatures, because adapter signature security definitions don't have any adapting oracle, and therefore it's not clear what happens after I adapt. So we can assume that we have an adapter scheme for a hard relation where if I learn one witness, I can compute all other witnesses of this user. Therefore, we have the following attack. A and B open generalized channels, then A simply refuses to answer B. So B has to close the channel by adapting. Therefore, A learns the witness of B. Then A can run the punishment mechanism against B because he knows all witnesses of B, and therefore can simply punish B. And this is still a secure scheme because no security game has adapting oracle. That was it on my talk. To conclude my talk, I want to say that in our work, we found that we can have stronger security definitions for adapter signatures. Using these stronger definitions, all protocol I proposed, I told you here, are still secure. And we also showed that the famous Schnorr adapter signature scheme is still secure in our updated definitions. Moreover, I want to make a little advertisement for my first paper that was published to a conference. I managed to publish my paper about Schnorr threshold signatures to crypto. If you want to talk about it, please let me know.
All right, thank you. So the next talk will be Mind the Gap, Breaching Language Security, Mandoc Research, and Cyber Intelligence by Cindy from the Federal State of Medical Board.
Hello. Today I'm going to share 2 real-world examples and discuss 2 real-world data sets. Why begin with crypto agility? In June of 2019, the closure of the Hahnemann University Hospital in Philadelphia resulted in the most significant graduate medical education displacement in history. The FSMB accepted training records under conditions of an unprecedented framework to receive data and issue a lifetime credential to physicians who are subject to the closure of Hahnemann. The FSMB issued these digitally signed documents with long-term validity to the displaced residents. This is why we're involved in long-term validity and how does that work with crypto agility. To understand the requirements of crypto agility, you need to get into present-day standards. From NIST identifying the post-quantum algorithms to ISO standards, they're not free in over 8,000 or 9,000 pages. A search for an open and comprehensive interpretation of these standards led me to the PDF Association. Exploring this association resources, a presentation by Dr. Tim Ellison is the link to the File Observatory for Secure Parser Development. From that node is the connection to SafeDocs and language security. Therefore, 4 degrees of separation. Specifications and secure parsers are the precursors to organizations pursuing crypto agility. Another application of signatures applied in yet another unexpected event. The COVID-19 pandemic and declaration of emergency lifted state licensure requirements. The Provider Bridge Passport was the second time credentials were issued to physicians using digital signatures for the purpose of practicing across state lines. The 3 domains in the Venn diagram are major contributors towards documents safety. They share common tools, data sets, parsers, and identify vulnerabilities. 2 commonly used data sets are from VirusTotal and Contago. Can the DARPA File Observatory add another dimension to available data? To bridge these 2 data sets is an experiment under investigation. This experiment, Dataset 1, is provided by Lockheed Martin Cybersecurity Research Fund, CIC dataset, which is from the Canadian Institute of Cybersecurity. The PDFs and curated CSV files are built from VirusTotal and Contigo. The second dataset is a subset of regression PDFs from DARPA's File Observatory, plus Google PDF from Regression and Malware Bazaar. Features extracted is complete using known tools, and the analysis of the features is preliminary. One of the features, the age of the documents, labeled create date, extracted directly from the PDFs. From the fill rates here, you can see that the CIC dataset benign has a 99% fill rate, and the worst is 25% from the malicious set. The other sets are ranging from 70 to 82%. The blue line, the CIC benign dataset, ends in 2012. The youngest in this dataset is more than 10 years old. The malicious data in red with less than 25% known create date has a higher distribution in 2010 than any other year and ends in the year 2020. The second real-world data set built from DARPA, the blue line is looking normal or trying to look normal and ends in 2020. Google PDF from Regression has a spike in 2015 like DARPA and ends in 2021. Malware Bazaar, a smaller sample size, most notably goes through 2023, which is intentional as an out-of-sample data set. Thank you for your time and enjoy the conference.
Thank you. So the next talk is specification and formal analysis of attestation mechanisms in confidential computing by Muhammad from EU Testing.
Yeah, hello everybody and welcome to my talk. Thank you very much. I would like to start by thanking my sponsors at Blockhouse Technology, Flashboards, and Convera, which enabled me to come here. Thanks for sponsoring this. And the idea of, oops, it doesn't seem to be working. Okay, so the idea of attestation is basically inside confidential computing that we have something, a workload working, uploaded to the cloud, and I want some kind of guarantees back from the cloud. So I have basically an attestation request which is sent over to the cloud. And then this is the evidence, attestation evidence, which comes back to me, through which I establish this process of trust. I verify that evidence and ensure that everything is correct. And then based on that attestation evidence verification, if everything passes, then I send over my sensitive data or secrets over to the cloud. So here, basically, the thing to understand is that the attestation mechanism is the trust-building mechanism, and if this is broken, you have no confidential computing at all. So this is really the heart of confidential computing, and which enables the confidential computing, and which gives you all the trust that the confidential computing is based on. So I will present here in this short talk 3 quick examples of Intel TDX and SCORM frameworks. Intel TDX is the VM-based solution of Intel, the next generation solution following SGX. And here is what Intel claimed that is the TCB of TDX. On the left side, you see that they have segregated what is trusted by the trust domain and what is not trusted. And what Intel never describes is what we have shown on the right, this chain of trust, which starting from the root of trust up to the trust domain, which is the VM, basically Intel's terminology. And Intel never describes what exactly is this chain and which can exactly falsify the claim of Intel that a trust domain does not need to trust only the TD coating enclave, which you see as the third entity on the left, trusted by the trust domain, but it also needs to trust everything which is in the trust, which is in the certificate chain, right? So which is a very basic thing that Intel has missed. So what we did was we reported it to Intel that this is really broken. It's not possible in any way to trust only the TD coating enclave and not the entities above that. Intel got it fixed. On the right, you see the diagram where Intel fixed it in their specifications. However, what Intel did was just to replace the PDF specifications which they had via the same link, via the same PDF. So you will not find the old specifications, which is the lack of transparency in this domain. The second example which I have here is related to the evidence. In the first slide, I showed that there is an evidence back from the cloud to the user or the relying party. And there are a number of fields, but on the left, what I want to focus on is the code structure, which you see in the going from outside of the yellow box. And there are two hashes, two arrows going outside. And what is really blows my head apart is that the hashes are sent over, but the data actually over which the hash is taken is not sent over as part of the code. And it's really amazing that how is the verifier supposed to calculate this hash? Getting only the hash does not make much sense. We reported it again to Intel, and what they did is the updated version on the right. And you see there that Intel said that, okay, now everything which is in this yellow box is sent over to the verifier. And then we asked, okay, so what sense does it make to have the MAC sent over to the verifier, which is outside this platform, and MAC works with the symmetric cryptography? How is the verifier actually supposed to have access to the key which will be used to verify this MAC? And what necessity is there to have MAC sent over to the verifier? And the third example that I have here is for the SCOAN framework, which is built on top of Intel SGX. Again, there are a few details, but what I want to really talk about is this thing of local attestation versus remote attestation. It's not a security flaw, but what the SCOAN guys did was that even if the two entities that you see on the top left, app service and that's the enclave, and the CAS enclave, the arrow between two denoted by phase 3, when they are on different platforms, it makes sense to do the remote attestation. But when they are on the same platform, same physical platform, it does not necessarily need the remote attestation. One can actually do local attestation, which is based on MAC, rather than remote attestation, which is based on signatures, and that is pretty much fast as compared to digital signatures. So we have reported this to SCOAN also. They are making the changes, and these are the key references that I have used in this presentation, and here is the link to our paper. Please feel free to talk to me if you are interested in this or you need more details. I will be very happy to discuss this. Thank you very much.
All right, thanks the speaker. So we have one last announcement from the Summer School of Software Security, but I'm not sure the speaker is here.
So yeah, thank you. This is going to be quick. I just wanted to make a quick announcement on the CASA Summer School on Software Security. I'm not sure, I guess this one is on the next slide there. Yeah, so the main idea is basically it's obviously software security is an interdisciplinary field. People obviously develop this, right? So you kind of want to keep humans in the loop as well as from the technical side, which is what the summer school is going to cover. So you'll see like talks as well as workshops on like software testing, fuzzing, automatic vulnerability discovery, etc. You can see a little picture of last year when it was on blockchain security. So that's not what we're doing this year, obviously. We'll have some speakers that you might have seen already around. So Fish Wang gave like a session share this morning, for example. We'll have some more people from the software engineering community, like Andreas Zeller and Eric Bodden. The entire thing happens in August, 14th to 16th. Unfortunately, for those of you who are attending DEF CON, this is immediately after. So you might have a little bit of an issue of getting there in time. And if you're not attending DEF CON, then that might be something you want to do. So it happens in Germany, in Bochum, which is where I'm from, an organization from both the Ruhr University as well as the MPI that's there. There's a few more obvious details that you might want to take a look at if the slides advance. They do. The target audience is not actually faculty, but it's graduate students, master or PhD. So if you are potentially considering a PhD, that might be something you want to attend. And then also, if you're an undergraduate student or you have undergraduate students that might find this interesting, you might want to send them there. So this is completely free attending. There's some financial support available if people need support for travel, etc. That does obviously come with some caveats, right? So you do need to apply for this. The application deadline is actually in 7 days, not in 8 days. And you need to submit a very brief motivation of 500 characters and basically your CV. And if you do have any questions on this, feel free to just either talk to me over the next days or send an email to our organizational people at the very bottom there, Johanna. And with that, I'm already done, and I think we're good in time for the TC meeting. Thanks.
All right, thanks, speaker. So that is it for the short talk section today. Thank you, everyone, for attending.